All right, hi everyone. So we're going to go ahead and get started here. So welcome to the first boot camp of winter quarter. My name is Carolina and I'm one of the co-bootcamp developers. So today we're going to be learning about some Python and how we can apply it to machine learning analysis. So I'm just going to go ahead and drop the link real quick for today's lesson.
Actually, Carolina, you can share this, and in the future you can also use just the UBIC website, because now the links for all the lessons are on the bootcamp page of the website.
Okay, sounds good. They were
Yeah,
updated.
and yeah, so just follow the first link. I just dropped the website link just for reference, but we'll be doing the machine learning and tumor classification Kaggle challenge, so you can go for that lesson link as well.
Yeah, so we're going to be working on lesson 8 today, guys. So Alex, do you want to take it from here?
Yeah, I can help with the account creation and stuff first. So yeah, so we're gonna use Kaggle, which is a kind of like a notebook. So if anyone has used Jupyter Notebook before, it's a kind of similar format where you have code boxes and then you can run the code and it'll visualize everything. And you can also input text. So it's a great way to present data. And it's also very easy to follow through with the data instead of just being in like a IDE or just looking at normal code where the visualization might be rendered separately. This kind of ties it all together. So it's very helpful. And so we'll start by, we're all gonna have to make a Kaggle account for this. But I just made one myself using my UCSD email and it worked. So follow the link to the Kaggle. Well, let me share my screen. I think that'll make it easier here. There you go. Can everyone see my screen? Yeah. Okay, cool. Thanks, Kevin. So this is the link. So if you follow the link to the workshop, the bootcamp website has this part already. So it might be easier just to follow this link. You can get to it from, if you go to the lesson 8, it'll be at the bottom. It'll be a link for this. The Zoom thing is covering my URL. So I could also just share it, but this is pretty much what we're going to be going to is, here we go, is this. But the bottom of lesson 8 also has this link if you're already on the page. And this is a Kaggle lesson. And so what you're going to do first, we're all going to have to log in or register an account, and it'll be just in the top right. And just click register, use your UCSD email. So I'll just wait a moment, a few minutes for everyone to do that. But it should just be at the top right, and then it'll go back to this page. And then once we're here, yeah, we'll keep going.
Yeah, so y'all can drop a thumbs up or something when you guys finish signing up.
So yeah, I'll check in about a minute, minute 30, see if anyone has any issues or not. And anyone who's already at this page, once you're here, you'll see in the top right, it'll say copy and edit. I already made one, but we'll click on that to have your own personal, like your own individual notebook for it. Oh, Cardiff. So I believe that Isham might be able to address that question better. Is the Google bucket might be just a different type of notebook, I believe.
Yeah, so Kaggle is pretty cool. It's actually meant for challenges more than just making your own projects. So the data that we're using in this lesson is actually not something we uploaded. It's there on Kaggle. It's open to anyone in the world, basically. Um, so yeah, Kaggle is basically for challenges, and you can even participate in those competitions. It's a great way to learn machine learning. In fact, I would say. Um, and part of the reason we want to stick with the Kaggle challenge format is so that you get to know and explore Kaggle.
It's also a little more accessible, I guess, than Jupyter Notebook, where you kind of need to initialize the environment, usually on your terminal or something. Okay, so can anyone speak up or put in their chat if they're not able to get to this page? And so I just registered, and then once it went back to the lesson, on the top right, the little black thing, it would say copy and edit. And so you'll click that, so you have your own environment for it. Okay, moving on. So yeah, lesson 8, machine learning. There's many different I guess, disciplines of machine learning, and it's a pretty exciting field. I guess, the two main parts is supervised and unsupervised learning. Supervised is more of a kind of training aspect of machine learning, where you give positive and negative input to the models so that they can more accurately identify things in the future. So it's predictive, and that some of the more advanced ones might be like image recognition, where like it's trying to find cats in a picture or different things like that. So a lot of captchas too that you use, where it's like, oh, identify boats in this picture. Those are actually used. That's a crowdsourced way to train some supervised learning models by Google. So whenever you're doing the captchas and it's trying to identify a picture, most of the time you're actually helping train a supervised learning model. So those are good for predicting new things, and you're kind of just telling the computer if it's right or wrong as you're doing it. Versus unsupervised learning is more about just recognizing patterns in the data with just kind of letting the algorithm do its thing. There's still a lot of parameters that you can input. And this is a broad generalization, but in general, unsupervised learning is more just using an algorithm to identify patterns in the data. Yeah, another one that isn't here besides clustering and dimensionality reduction is self-organizing maps. That's one that I use for my research, which is kind of a form of dimensionality reduction and clustering. And it pretty much just, if you have a big data set and it can be high dimensional, you start with a bunch of random points, and pretty much just through a bunch of iterations, the random points will get closer and closer to represent the data set that you gave it, in a way where you can have a really high, like the thing I use has I think about 6 million data points, but the self-organizing map only has 40,000 units. And so it's a way to just kind of, and each one has a bunch of different points inside it. So it's just a good way to turn a very large data set into a smaller, simplified version. And you can also use that to, if you have a new input, it'll try to put it into one of those units. So it's a way to classify or cluster as well. So that's just one other example. But for this lesson, we're going to be going over, well, first of all, I guess I should have mentioned this. So yeah, supervised uses a training set with correct inputs and outputs to predict outputs for test data inputs. And so yeah, classification in this format, we have features and outputs, maybe binary like yes or no, or like if it is a cat, or put it into other classes that you had pre-trained. And then regression, where you have a bunch of independent variables and you have a dependent variable, which is continuous. So you can basically apply new inputs to it as well and see if it fits that dependent variable, I believe. But there's also unsupervised learning, where yeah, you find patterns among inputs and you don't really have labels. You're not telling it what it is beforehand. You're just letting the algorithm run. And again, you can do clustering, where you find groups within data. And for bioinformatics, you can do phylogeneity or dimensionality reduction, where you might have very complex data and you want to find a simpler way to express that data, or maybe even see what the patterns are, what's really important inside it. And so we're going to start going here with the notebook. So this is just some kind of housekeeping. So we're going to run this first here, which is going to import the libraries that we need, as well as set the directory, I believe. So we'll just press plus here. I'm not sure, what is the, is there a...
Shift plus enter. Shift plus enter, or on Mac, Shift plus return, yeah.
Okay, cool.
So to run the cell, you can use Shift plus enter, or you can click on that play button, whichever is more convenient. With Shift plus enter, that's more convenient. Yeah, and you have the imports here, and then you're just getting the files that are already on the kernel, I guess, because it's a Kaggle notebook.
Thank you. And so you can see the output normally. If there is any output, it'll show up below the cell. And so I just printed the working directory. And so you can see we are here right now. And now we're going to pull some test data. And like as Sean said, it is coming from Kaggle. So it's kind of nice. And so we'll load that. And so this is assigning it to some variables or some objects. So now we can actually use them. And I guess just to see what data we're using, we're gonna use head, which is a nice function just to kind of peek at the data. So we can do it for the first. This is the testing data set. And so it looks like it was many other rows, but really what this is good is, okay, Carolina, this is helpful because we can, you can actually see what is going on this way. Like, even though there's many more rows, this is the important thing. So yeah, I'm gonna pass it to Carolina right here. Should I stay on the screen, or do you want to share your screen?
Yeah, maybe I should share my screen so it'll be a little bit easier for me to follow along.
Okay. Will it let you take over, or do I need to stop?
I think it will let me take over. Yep. Okay. So, all right, kind of like how Alex mentioned, let me just run also my code here. Also, if you guys are following along, make sure you run every cell of code, or else if you try to run the later cells, they won't actually work. So just double check that you actually do that. So like Alex kind of explained here, we're just taking the first 3 lines of each CSV file that we imported. So as you can see here, we got the first 3 lines of the train set, and then we got the first 3 lines of the test set. So then for each of those 3 data sets, we're going to get the number of rows, the number of columns, and also the titles of each column. So we can just run this cell here, and then that'll print out everything that we wanted, being the titles and the labels. So then again, we do that for each data file that we imported, train, and labels. In here. Okay. So then now that we basically have all of our data and we've kind of organized everything, we're going to go ahead and start cleaning up the data that we were given. So after running the head function on the files, so you guys can see here how we got this pretty big chart here, we don't really need a lot of the data that's actually presented to us. So we're going to try to clean up and try to minimize the amount of data that we're using. So we're going to do that down here. And this, sorry, can you guys hear me by any chance? Yeah.
Yes.
By the way, feel free to just unmute yourself or use the chat if you have any questions about the dataset. Okay, now Carolina froze, I think. Yeah, she definitely did. Okay.
Yeah.
I guess for now I can carry on. I think, Alex, you might want to stop sharing if you haven't already. Have you actually?
I stopped.
Okay, cool.
It still let me continue sharing, so I'm not sure how it prioritizes it.
Yeah, because I enabled multiple participants, but then it becomes too heavy, I think. Right, so that's not good. All right. But basically, okay, Carolina's not here. But one good thing to know when you get your data is how it looks, right? And that's what we were just exploring. That's what Carolina was trying to explain. Couple of things that can be helpful to see is first just how it looks, right? So I'm gonna edit this. Now, how many rows does the trained dataset and how many rows does the test dataset contain, right? That's a good thing to know. Kaggle has already separated the trained dataset and the test dataset, but the Y labels, right? They are all present in labels, and we'll just now see what the labels are, what the train is, what the test is. So if I run this, okay, there we go. So in this table, you first see the gene description for each gene. So each row is one gene, all right? And that's the gene description for that gene. Then the gene accession number for that gene. And then what we have are the expression levels. Now you see that there are some negative numbers here, and one might wonder, what are negative expression levels? How did we get those? And basically what this means is we basically got the number of reads coming from each gene, and we don't need to get into the RNA-seq details. Basically, we got the number of reads from each gene. Higher the number of reads, higher the expression. And then we normalized those values. This lab activity is based on a paper. So the paper probably discusses more about how they normalized it, but essentially each column, right? Each of these, I think 36, 30, 38, something, each of these columns is actually a cell, yeah, or a sample, I'd say, yeah, a sample. And the column, these numbers indicate the gene expression for that gene in that sample, right? So for example, minus 95 is the expression level, the normalized expression level for this gene in the 30th sample, right? Yeah, there are 37 samples, I think, 37 samples, I think, in the training data set, and some 39 to 62. Yeah, we'll sort these columns and we'll see how many actually samples there are. But you can see that besides these expression levels, there's this useless column which has just A's, right? We want to get rid of these columns because they don't have any meaning for us. And besides that, we're going to be using only the expression levels in our data set, in our machine learning model. We don't really use the gene description name or the gene accession number in our model, right? Um, our model is going to get the expression levels and it's going to predict whether it's um, an AML type of cancer or ALL type of cancer. And that's what the labels dataset contains. So the so yeah, this cell, I think, so this shows what the labels table looks like. So each row now is a sample, all right? Each row is a sample, and the cancer column shows which type of cancer it contains. Um, so you see ALL like that. Um, and that's it basically. So there must be some AML values in between, I think. Let's see, cancer. Uh, if I print the values, you see ALLs, then you see AMLs, ALL, AML. So ALL and AML are two types of cancer, and the full form I can't recall at the moment. So acute lymphocytic leukemia, and then AML is acute myeloid leukemia. And we have um, some samples that are ALL patients and some samples coming from AML patients. All right, we want to predict whether for a given patient, for given gene expression levels, whether the patient is more likely to have ALL or AML. Because for background context, these two type of cancer have similar symptoms and can be hard to distinguish sometimes. So the machine learning approach helps identify um, which type of cancer is most likely depending on what genes seem to be highly expressed or lowly expressed, right? Any questions so far? All right. So now we're going to start with data cleaning, all right? And we have some 4 steps for the training data set. First of all, we don't need the columns that have the heading as call point one, whichever columns whichever columns heading starts with call, we don't need those columns in both training and test. So this column is useless, this column is useless, this column is useless. So this is training and this is test. We don't need those call columns. That's the first step. All right. Now, gene descriptions and gene accession numbers are useful information, but not for the model because we are trying to make a model that takes in only the gene expression levels for that patient and gives us the cancer type. Then third step is right now, if you check out these columns, right? So we have first, third, well, this is the test one. So in train even you see 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. You'll see that, okay, I guess in training they are sorted, but in testing, if you'll see, these are not all sorted because you see, so we have 66 here, then the next one is 63, and then 64. So these are not sorted. So we want to sort these columns. Just because it doesn't really affect much, honestly, but it just makes the data look, I guess, neat, and it's a nice way to represent your data. The fourth step that we want to do that's pretty important too is now, what is more intuitive? Having each sample as a row or having each sample as a column? What do you think? What do you all think? Well, how do you visualize data usually? Do you see samples as rows, or do you see samples as columns usually? So I'm getting some responses in the chat. Um, so okay, Cardiff and Kevin like columns for some reason. But when we look at a business record, for example, don't we usually first see like a name of a person, their age, their address, and stuff like that? Yeah, I know why you like columns, because you don't want to deal with the transpose and code for that. Yeah, but also when you put the model in, when you put the data in the model will expect the rows to be different data points and each column to be a feature. So each patient has to be a row, and each feature, which is each gene expression level, each gene has to be a column. So I'm sorry, Kevin and Cardiff, we'll have to do a very important and very lengthy step, which is gonna be basically just putting a dot and a T. That's it. So let's work on all these steps now, right? So I have the code here, but I'm just gonna show you like I'm gonna write the exact same code but step by step. So right now we have train X, for example. All right, now we want to remove the call columns. So we can select particular columns in a data frame by just giving the list of the columns you need in here. All right. So the columns that we need are going to be all the columns that TrainX has. That's how you get all the columns, right? So for column in TrainX columns, if that column, column does not start with call, like CALL call. So if not call dot starts with CALL, I don't want those columns. So this is what a list comprehension is. And now it's actually, this is what completes it. So for all the columns, if they don't start with CALL, I'm going to put them into my list. So that's going to be what all columns. That's going to be the gene description, the gene accession number, 1, skip this, 2, skip this, 3, skip this, 4, skip this, like that, and so on till the last column. Now, that completes the first step. Now, I don't want the gene descriptions and accession numbers either. So I'm there's different ways to do it, by the way. You can also say call starts with call or call starts with gene. But what I'm going to do is just in this columns list, I'm just going to I'm just going to start with index 2. So that's going to start from the column after accession number. So for train, it's going to start from this 1, and for test, it's going to start with 39. All right. So this is the list of all the columns. So this is the list of all the columns that I need. Now, these are not sorted, so I'm just going to sort them using their integer value. Right now, as you can see, these column names are in string format. So I want to get the integer value, and how I do that is, again, you don't really have to do this necessarily, but it's just good to know and explore how sorted function works. So sorted function takes a second argument, a key. So how exactly, like what value do I use to sort something? And that key is going to be a function. You can give any function. What I can use here is just the int function, and that should do the trick. So int function, basically how that works is if I have a string, say 12, but in string, if I use the int function, it's going to give me the integer value of that string. And that's why key equals int will do the job. And yeah, this is going to be the sorted list of the columns. And this is the trainings table, but with selected columns. Now, what's the last step? Transpose. So for transpose basically means that each row becomes a column and each column becomes a row. So the row headers will become column headers and column headers will become row headers. So instead of having 7129 columns, I'll have 7129 rows. And yes, Cardiff, the one-liner is going to be super useful. So .t gives the transpose of the table. And now this is going to be my new pre-processed, not pre-processed, I would say clean, I guess cleaned training data set, training table. And similarly, I can do for test. So I just change trainx to testx and here as well. I'm giving slightly different name just so that I can run this again without losing my variables. And now I'll be using train_x and test_x for my modeling. I won't be using the original tables anymore. Besides that, I am also just keeping a table of just the gene descriptions and gene accession numbers using just the first two columns for all rows. All right, and that's going to be in genes. Actually, yeah. So all rows and first two columns. Yeah. So run that. And now let's just maybe take a peek at what that gives us. So trainx is going to be this kind of matrix. That's 38 rows now, right? So 38 samples, sorry, 38 samples and 7129 genes. So this is an example of a broad data, right? Like a data that has more columns, more features than samples. And that's why it's very hard for a single person to just find a few biomarkers because there are so many genes, right? Okay, so this is the training data set. Make sure you follow along. Let me know if you have any questions or if you've been able to catch up so far. And feel free to unmute yourself at any point.
Hey, Sean.
All right. Yeah, Kevin.
So the code we have in this notebook itself, those code I ran them, but they don't really work. I mean, they compile, but they don't really get rid of the call column.
So in which cell is that?
I'm sorry?
In which cell is that?
Right after the 4 are those columns in order, like number 18, I think.
This one?
No. It's the one that came with the document.
Okay, so that should be, I guess, this one?
No. Okay, I'll do a screenshot, I think, if that works.
Yeah, sure. Yeah, or what's the code maybe? What's the code? You can just paste the code on the chat maybe, that can help.
Oh, yeah, that's right. Okay, 1 second. Here.
Okay, I see. Oh, so basically it's this cell. It's basically this cell, but the old version, right? And that's also fine. So what's the problem with this now again? Is it not running?
So I ran it, and then I also I typed train X, but the stuff it showed me are with the call columns. It didn't get rid of those columns.
It didn't get rid of the columns. Make sure that you're checking for train_x and not just trainx, because
maybe that's
yeah, that might be the reason. I actually,
there we go. Yeah,
I don't know. I had a hunch that I think it's going to be about that because it can be a bit confusing.
Oh, sorry. Yeah. You named
It's my
that.
fault. I could have probably gone with better names. Maybe like raw trainx for this one. Yeah, don't be like me. Name your tables and variables better than me.
All right, thank
And
you so much.
yeah, that's a nice question though. That was a nice observation. Yeah. All right. Anybody else has any other questions? All right. So this was the training and testing X part, the features. Now we're going to move to pre-process what we are going to predict, the labels. All right. So right now what we have as labels is just a table of each row as a sample. And this has both training and test samples. So you can check, there are, I think, I keep forgetting how many rows each of them has, but there are 38 samples in training dataset and 34 in testing. So the first 38 rows of labels table is the training dataset labels. And the last 34 rows are the testing dataset labels. All right. So we want to keep them separate as well. We want to keep the training by separate and the testing by separate. So what we do is we get the first 38 rows, all right, um, in the cancer column. And then we say if that is AML, then, right, if that is AML, then as type integer. So what that does is if it is AML, it returns a 1. Okay, it puts this as 1. And if it's an ALL instead, then it puts it as 0. And the same for testing. So this is the first 38 rows that goes into training by, and then the rows following 38th index, that's going to be the testing data set. So testing by, right? Same code. So get those rows in the cancer column. If it is ALL, then 0. And if it's AML, then 1. Does this also make sense to you? So this is assigned to train by, and then the next one is assigned to test by. Any doubts? We can quickly check what that looks like. So train by is zeros followed by ones because all the ALLs are the first 26 rows and the AMLs are the last few rows. All right.
I have a question, Ishan.
Yeah, Alex.
So if you had, let's say, 10 different cancer types, could you
Sure. Yeah.
continue doing this up until like 0 through 9? Or does it work best if
That's a great question, Alex. And actually, multi-labeled classification is very similar to the binary classification that we are doing. You can have labels from 0 to 9, but here's my question. What if I wasn't predicting some classification, some classes? What if I was predicting a number? How does the model know whether you're giving a quantity or an index? Like, what if I was predicting like some score out of 10, for example, right? So the way to differentiate for 10 different classes, 10 different things you could predict, like 10 cancer types, is instead of using 0, 1, 2, 3, and so on up till 9, use 9, like use an array of 9 binary numbers. So instead of a 0, you could take a bit array, you could take like an array of zeros and ones. So the array for like cancer type 3 could be 0, 0, 1, 0, 0, 0, 0, like that. And then for cancer type 5, it could be 0, 0, 0, 1, 0, 0, like that. And that's actually even more advanced, and that's a great question, Alex, because that's the exact same algorithms that we are using, with minor tweaks in this code that we'll be using. You can do exactly that as well. But instead of having zeros, like 0 to 9 score for cancer type, you should do an array of an array of 9 digits, each digit being 0 or 1, so that you can keep them independent of each other.
Okay.
Yeah. Yeah. Right. I'm gonna look at the chat. How does the code assign each row as 0, 1? Simply because of the syntax x, y equals stuff. So I can kind of break it down actually. I think by x, y equals stuff, what your question is, what we're doing is actually this. So train y is this, and then test y is this. This is what we are basically doing. Python is smarter than this. So what it allows you to do is you can assign two different variables with two different values. So I can say like a comma b equals 4 comma 5, and then if I ask what is a, then it'll give me a 4, and if I ask what's b, it will give me a 5. So that's exactly what I'm doing in this cell as well. I'm just signing the first 38 rows um, the integer value of if they're equal to a male, um, as train y, and the integer value of whether they are a male in the 38 onwards rows as test y. Again, good question, Cardiff.
So
Sometimes
it's
I
converting the true or false to just binary.
Exactly. So if I did not have
False.
the integer conversion, it'll give me false because this is ALL, so it's not AML, and this will be true. But I want numbers, so I'm going to just use as type int, which is basically, I think, a NumPy or pandas function, and it converts false to zeros and trues to 1. Great questions. Keep them coming. I'm loving this. Any other questions? All right, then. So now we come to our first machine learning algorithm, and you're going to enjoy this. This is kind of the meat. Um, what is dimensionality reduction, right? What we have right now is some 7,000 different genes. If we wanted to just visualize the data, right? So patients that are similar be shown together closer to each other. Patients that have different expression profiles be farther from each other. How do we show that on the data, right? How do we show that data? So for that, dimensionality reduction basically reduces any given number of dimensions to lower number of dimensions. What this figure shows here is something you can probably understand better. So suppose I have this data in 3D, right? PCA can basically take those 3 coordinates and show what they would look like in just 2 dimensions. And that'll explain the same variation, which basically means that if you find any pair, if they are similar to each other, if they would be closer maybe in the 3D, then they would also be closer in 2D. And if they're farther in 3D, then they would be farther in 2D as well. And just now you can sort of like extrapolate this concept to our data set. So instead of going from 3D to 2D, we are going to be going from 7,129D to 3D, or 7,129 to 2D. So this is 3D to 2D. We're actually reducing 7,000, and it can be any number of dimensions that you need. It's gonna find sort of axes, this as it shows here, first principal component and second principal component, that separate the data most effectively. And since this is going to 2D, it's going to find two such principal components. We're doing both. We're doing 2 components and 3 components. So PCA basically finds these principal components, right? There are other dimensionality reduction algorithms, and UMAP is very popular nowadays, especially with single RNA-seq data you might have seen in classes or labs. Um, People, what they do is they would get these single RNA-seq levels of um, single RNA-seq expressions from different cell types, and then they would plot the data. And what they would find is on the UMAP, you'll find different clusters formed by different cell types, like cells that are similar to each other would be forming one kind of cluster, and cells that are of different types, they would be farther and forming different clusters on UMAP. And that is very interesting indeed. Even our activity is actually pretty interesting, I would say. So while this algorithm and the math behind is something even I can't very fully explain at the moment, honestly. I don't remember how the PC algorithm exactly works. And I don't need to, because scikit-learn package has these black box implementations. So we can just use the implementation and we can import this package PCA. So what you do is you first make an object by calling kind of like a constructor for PCA, and you give the number of components. Now this reducer object, right? This, you can name it anything you want. This object can be used to fit to data and also transform given data. Um, and the function fit transform, what that does is, for the reducer object, it takes in given data and it makes that model, makes the object model fit to this data, and then also returns the principal component. So since this object is made with 3 components, TrainX PCI3 will have 3 principal components. Similarly, you'll have 2 principal components for TrainX PCA2, right? So it's probably easier to look at the code and try to understand instead of um, trying to verbally explain it. And what you'll notice is this is very similar to what you might have used for other scikit-learn packages. We had a linear regression workshop, I think, last quarter, and we'll be using scikit again for classification further. All right, so we can now look at the principal components. So just run this. It'll take some time to fit and transform. Now let's first see what they let's just see maybe train X PCF3 for now. Let's just look at that. So what do you notice? What's the shape of train X PCF3? Can someone put that on the chat or like speak up and tell? What shape do you see for PCA for the train X PCA3? Cardiff says 3 by many rows. That's very clever, Cardiff, but I would like to know how many rows and why that many rows, maybe. What each row basically stands for. That said, Cardiff, you are right. It is 3 columns in this. And if you'll also get PCA2, you'll see just 2 columns here. 38 rows. That's exactly correct, Cardiff. Each row basically stands for each of those training sample that we had. So essentially, it's the same samples from the training dataset. This is an array containing the principal components for the first sample, then second sample, third sample, like that. So since we had 38 samples in the training dataset, and we have the principal components for training dataset here, it has 38 rows, and you'll see same 38 rows for PCA2. Another thing you might notice is that this column, right, -4, 1, 2, 186, this column is the same exact column as this column here. I can't show the whole thing, but basically the PCA2's first column. Similarly, the second column is also the same. And the reason is because it doesn't really change when, like, it doesn't matter how many principal components you're getting. The first principal component and the second, nth principal component is always going to be the same for given data. Um, so if you get 3 principal components, it's just going to make the principal component 3 as well. But the first 2 are going to be the same if you got just 2 principal components. So that's another good observation, right? Yeah, and for each sample, we can now plot them easily because we know how to plot 3D and 2D data. 2D we have done, in fact, using matplotlib in like earlier, I guess, and you can try that on your own as well. I'm gonna run the plot and show the plot for 3D. So 3D as in like 3 principal components. And you'll see what I'm doing here is I have the figure, the axis, and projection is 3D, which basically makes it a 3D graph. And in my scatter 3D, I'm putting the first column, all the rows first column as my X, then Y is the second column, Z is the third column. And the color, so C is the color, that's actually train Y. Why I did that is what this graph now shows me. Purple is one cancer type and yellow is the other cancer type. Now I don't exactly remember which one is AML and which one is ALL. We can probably check that. We can probably we could probably label that too, but or I guess we can just check what the first one is. So this is -4128435, and we had ALL values in starting, and then we had AMLs. So -412. So -412 is along here, and 8345. So I think that's this point maybe, um, or maybe this. Yeah, not really sure, but basically one of them is ML and ALL. Important observation here is that how separable, how linearly separable these two classes are. This data set, you can in this data set you can distinctively see ALL apart from AML. So that's a good sign. That means we can easily make a machine learning model that can classify and predict the correct class for ALL and AML. Had this been fuzzier, then you would have to probably go for more sophisticated classification, or maybe it's not very separable. It's not very, like it's hard to make out what the class is. But since you can clearly see the purple apart from the yellow dots, it means that you can easily separate them using classification models, right? And you can get the 2D plot on your own. And there are similar libraries for UMAP and TSNE as well, so you can try that as well. Yeah, PCA usually works better for linearly transformable data. UMAP is actually more sophisticated, more robust, but more specific to certain other data types. That's why UMAP is more suited for single cell RNA-seq. And probably even this data set, maybe UMAP would have been a great idea. So you can try that as well. All right. Any questions? Does it make sense how we're using this PCA algorithm? Any questions about that? What's the C part? So C is the color. C is basically the color here. That's the color argument for plotting the scatter plot. And I'm using the labels, the Y labels of the training data set here, because that then I can separate ALL from AML on the basis of color. So in this plot, purple is, suppose purple is maybe AML and yellow is ALL, or vice versa. Yeah. All right, so any other questions? Does it make sense what these PCA are trying to show and how this PCA exactly works?
And I believe, please correct me if I'm wrong, but for it to get these values, it comes up with a ratio to multiply by for each of the dimensions for each sample. And that's how it's able to convert it.
Honestly, Alex, I don't remember how PCA exactly works, but this plot is basically just the principal components plotted, just the principal component values exactly. So like this, these are the XYZ coordinates in this plot.
Okay.
Yeah.
It's a very
Yeah,
useful
but,
tool.
it is very useful. Yeah. But if I do remember correctly, I think it's somewhat similar to, I think it's similar to k-means clustering, but instead of using the clusters, it just uses like the principal components, the axes. Yeah. Not k-means actually, but anyways, yeah. Yeah, I think we can move to the classification part if we don't have any further questions. Right, so this is the final task. Now we are actually gonna make a model that takes in expression levels and gives the predicted labels. Carolina, would you like to continue?
Hi, yeah, I actually had to join in through my phone. My laptop is
No,
not working right now. I'm
not
so
working. Okay, no worries, no worries. I can do it, I think.
okay.
Yeah, let me just grab a simple. Yeah, feel free to read classification, what classification is, as the text says. All right, so classification is, as Alex told us at the beginning, it's a supervised learning model. So we are predicting a class, like predicting a Y. And here Y is just 0 or 1. 0 if it's 0 if it's ALL, and 1 if it's AML. So we are performing binary classification again, as we had brought out earlier. Out of 2, AML and ALL, we're predicting just out of these 2 possible cancer types. And then we get the probability. And as you know, probability is between 0 or 1. If it's closer to 0, we'll predict it to be a 0. And if it's closer to 1, it's going to be a 1. Now, how this actually works is that can basically vary depending upon the model that we use. There's different models. Even in this activity, we do have different models. We have logistic regression, right? And then we have k nearest neighbors. Unfortunately, with the time constraint, we can only cover one of them. And there's a reason that I would like to continue with the logistic regression for now, and I'll discuss that soon. But for now, let's try logistic regression. One of the reasons is that it's very popular, one of the most popular classification models, and it gives great performance for our data. So logistic regression, you might have heard of linear regression from our previous workshops or some other courses that you might have taken. Linear regression, basically what that is, you have a plot and you have some data points, right? And they might have positive or negative correlation. Um, and what you try is you try to predict this this equation, the straight line equation that seems to be explaining the data points distribution the best. So in that, basically, you are trying to reduce these kind of errors, right? The error of each point, the deviation of each point from the line. You're trying to minimize the mean square error of all these data points, which is one possible way to do it. Um, Right. And very similar to that is logistic regression. Technically, you could also use linear regression for this, but it's not a good idea. Linear regression goes from like an intercept, which could also be a non-zero intercept, by the way, an intercept to infinity, right? Or it could be from a intercept to minus infinity, depending on the slope. But essentially, we are predicting probability, which should be between 0 or 1. And that's what the sigmoid function or the logit function really comes in handy with. So this is what the sigmoid function looks like. So basically, a sigmoid function is 1 over 1 plus e of minus x. That's what the sigmoid of x looks like. And the graph, yeah, the curve given by this function is an S-shaped curve as shown here. And it's like point of inflection, I guess, when I get technical, is at 0. So it's the same absolute, no, not the same absolute value, but it's symmetrical around x equals 0. Here they have shown z, I'm using x, same thing. But if you look at the positive part, right, it's going to predict within these different bounds. And right now the probability, as you can see here, is going to go from 0 to 1. That's what the logit function is. It cannot go beyond 0 or 1. And that's of great advantage because that's why it helps with classification, because we are predicting probability. And the number we're predicting has to be between 0 and 1. So the calculus part of it, you again don't need to understand that. But one thing that I would like you to understand is that what we're doing essentially here is that we get a z that is equal to some intercept, so b maybe, plus a weight, all right, multiplied by the feature that we are using. So like ith gene, for example, in our data, and that's for all the different genes. All right, and the model is trying to tune the wi's, the weights, that is, these weights. All right, so I'm just gonna complete this, I guess. So we're trying to find these wi's. When we put them into the sigmoid function, that is 1 by 1 plus e minus z, the like the probability distribution best matches with the data points distribution. And yeah, it can be about hard to understand. We can talk a bit more about it, but I think the best way to understand is to actually see it in action. Right, so let's start coding now for that. And we'll come back to the weights later. Wait, I think, oh no, I think some cells of this notebook are actually, they've somehow been shifted down. I'm so sorry about that. So actually, I would like you to run, wait, where is it actually? Never mind. Yeah, it's this one. Never mind. Sorry, I'm blind. Yeah. So we import the logistic regression model, we make the object, and then we fit the model based on the training X data and the trainings Y labels. So just run this and that just trains the data. So that's training the data, and that's why we use the training data set. Since this is classification now, we test our data using the testing data set, so that you have the training data set that you know from before, and testing just tells you how good your model is. So that should always be on some data that the model hasn't seen before. Okay, testing data set has to be different from training, so that it's tested on something that it hasn't seen before, right? Because we're going to be deploying the model or using the model on some data that the model hasn't seen before. So get we should like assess the model, how good it's performing on some unseen data. Okay, so training data is the seen data and test data is the unseen data. So this is what's going to train the model. And now I'm going to actually break this down, and I can put the code on the chat as well. But essentially how you get the predictions for your test dataset is using this predict function. All right. And it takes as input your testing data, right? So it's going to take the expression level matrix for testing data, and it's going to return this array of zeros and ones. And this is what it predicts as AML or ALL. And you can see it has a lot of zeros before, which makes sense because in testing data set, we had AMLs before and ALLs later. You can see this here. So if we get the test Y, right? I mean, I can print this as an array to make it look similar to this. And so 0, 0, right? So the actual value is a 0, and the model is also predicting as a 0. Model is predicting same as here, same for these. It's predicting correctly for the first 7, 8 values, but then it makes an error. Actually, it's an AML, while the model is predicting as actually it's ALL, a 0, and the model is predicting it as a 1, so AML. So it's making an error, and it's bound to happen. If you look at it, it's performing pretty good for a decent number of samples. And how we assess it, there's different way to assess a model. Most popular way to assess the model, your primary way sort of to assess a classification model, is to use accuracy score. Accuracy basically means how many times are you right, which means if here it's a 0, it should be a 0 here. And if it's a 1 here, then it should be a 1. I think I have this sort of like a table later, but basically this is this table is the confusion matrix that we usually show. Positive means 1 and negative means 0 in this case. In this case, the negative class is 0 and positive is 1. So true positive means the actual value is a 1 and the model predicts it as a 1 as well. True negative means the actual value is a 0, that is a LL, and the model is also predicting as a 0. Now, false positive means, as you might have heard, false positive for different things like vaccines and stuff. False positive means that actually it's a negative, but the model is predicting wrongly as a positive. So actually it's a 0, so ALL, but the model is predicting as 1, AML. And for false negative is the opposite. So the actual value is AML 1 and model is predicting as ALL 0. Now accuracy is the ratio out of all the samples of the true positives and the true negatives combined. So these two are the correct values, right? So these are how many times was the model correct. So accuracy score is true positive plus true negative divided by the size of the sample. All right, I just wanted to kind of also briefly touch true positive, true negatives. It's good to know, although we don't have enough time to cover that part. Okay, so we can get the data imported. I imported it. I think I did not import it actually. I need to import it. Yeah. Um, yeah, I think I have it down here. Yeah. No, not here. And I'll put it on the chat too, maybe, but just bear with me for a sec. Oh, yeah, here. So I'll put this on the chat as well. So you need to import this before you run accuracy score. All right, so you print the accuracy score with that for, so first you can check the documentation too, but essentially you give the predictions and then you give the actual values. And these two are going to be the input for the accuracy score. And that's what we are printing. So accuracy score with the predictions as first argument, and then the real test y values as the second argument. And I'll come to the second piece of code in a sec, but let's just look at that. So accuracy score is actually pretty good. It's 97%. And as you might see if you follow along and try k nearest neighbors, the accuracies, I can just quickly run this actually without really explaining.
Just a quick aside, I believe the k nearest neighbors and the logistic regression may have been switched that we shared.
Oh, in your version, is the k nearest neighbor before logistic regression?
Yes.
Oh, that's the original version. I thought it's saved with the logistic regression first. I hope everybody's able to scroll down and find logistic regression, because I'm not covering KNN because of the time constraint. But I just wanted to show that these are accuracies for different models using k nearest neighbors, and none of them actually beats the kind of accuracy that logistic regression gives us without any additional steps. So here you can see basic, then something called standard scale, something called robust scale, something called PCA reduced. But all these accuracies are nowhere, well, somewhat near, but not nowhere near 97%, which is what logistic regression gives us. So pretty good. 97% of the time we were predicting the right thing. It's pretty amazing. All right, so any questions? I hope everybody is able to understand what logistic regression is trying to do essentially, and what the accuracy score is used for. You can also get the confusion matrix, by the way. You can get the confusion matrix for using the same arguments. First the predictions, then the test y values. And we have 1 false negative, no false positives, then true negatives 14, and then 19 false, true positives. So I think the 1 false, so we're actually making only 1 error, which is pretty amazing, right? I mean, it's only out of what, 33 samples, but still pretty, 34, I guess. 34 samples, 1 is wrong, so that's pretty good.
The version that at least I have might be a little different for comparing the accuracy, but comparing it to the k means using TCA or just using a robust scaling, looks like it only gets to about 93%. So
93, I mean, it's possible that the scaling changed and maybe
it might have been 91. I was just looking at actually the figure that is right below there.
Oh yeah, it's 91. Yeah, I think it should be the same because none of them seems to be randomized, so it should probably give it the same accuracies. Yeah, we won't be able to cover what standard scale and robust scaled exactly is, but think more importantly, so in this, the paper that this data came from, they had made this figure actually, which you might even find till this date. So it's the Golub et al. Paper, and it has, I think also, who's the like scientific advisor in White House? Eric, no, not Eric. Man, he's a legend. But there's also Mizerov, Jill Mizerov, who's an amazing professor at UCSD now. Back then, she was actually working at MIT. And this is about basically cancer type prediction and molecular classification of cancer, class discovery. Yeah. So if you check the figures for this paper, one legendary figure is actually this. So what they do in this figure is they show, so each row is a gene. And in the first half, they show the genes which have higher expression for ALL, lower expression for AML. And then they show some genes which have higher expression for ALL and lower expression for AML. Opposite. ALL, AML high expression and ALL low expression. Now, we're gonna try to reproduce this figure. We're probably not gonna get the same exact genes. I don't know what exactly genes actually they show even. Actually, I think I have something on the chat. When did we cut the number of rows to 38 again? I think we did that, Cardiff. We did that only for the labels, by the way. 38 is so as to get only the training ones, because the first 38 were training data set. And then after 38, we had testing. So that was probably when we got the labels separated into train Y and train Y and test Y. Yeah.
And
Yeah,
you
so
can
these
see that
are,
in the brackets. It'll be like colon to or something.
yeah, colon 38.
Colon to
Yeah,
bracket and then 38 colon bracket.
38 colon. Yeah.
Yeah, just so you see where
Um,
it was.
yeah. In fact, yeah. So we're trying to basically get the genes that are good at differentiating between ALL and AML. So each column is a sample, and this shows the genes that have really high expression, like distinctively high expression for ALL types, and distinctively low expression for AML, and vice versa, in the bottom part. So this is super interesting. And how we're going to do this is, we have the logistic regression model now, right? Remember those weights, right? So sigmoid function is an increasing function. So if the sigmoid's prediction is a high number that is close to 1, the z that we put in, that is intercept plus, well, I guess b, which is bias, not intercept technically, but bias plus weight, multiplied by gene expression level, that essentially that b plus, those wi xi, these these weighted expression levels, this z, which actually is the input for the sigmoid function. I think bias might be actually 0 in this model by default. Basically this. So if the weight of a gene is a higher number, right? If it's a higher number, it's going to increase z. So it's going to increase the predicted probability. And 1 means AML, right? So if 1 is AML now, higher weight will make it more, like, will increase the probability, and then it will be more likely to be AML. That's what the model is going to predict, right? So the gene with the higher weight will be associated with AML, and gene with the lower or more negative weight would be associated with ALL. And that's what we're going to use. So we're going to basically sort the genes by the weight in the model.
and we can get those weights using coefficient. So the model that we have, our LRCLF, this object that we had created, right? So LRCLF dot coefficient gives us the weights. Now this is going to be a list of, you can check it out. Um, it's going to be this list of weight of each gene. You can check the link, it's okay. Yeah, I know. You can check the shape, not the length, I guess. So yeah, 7,000 genes. So it's transpose actually that will give us, transpose of this coefficient is going to be, okay, never mind. So basically it contains the weights for each gene, and how we get it, we use squeeze function to just get a list of just the weights, to remove this double bracket structure like this, to change it from a column to an array. So we use np.squeeze for that, right? And that gives us these weights. Right. Now, what we want to do is we want to sort this, but we also want to keep track of the order in which they appear. So what we do is we first enumerate these weights. And what that gives us is, if I convert that to a list, for each of the gene expression, the weight, basically, for each weight, it prints kind of like an index with that. All right. Now, if I sort this, right, if I sort this using the sorted function and give the key to be, so the key is going to be basically a lambda function. Okay. You can even make a new function if you don't understand how a lambda function works. But basically, trust me, what this is going to do is it's just going to sort this array based on just the weight. Instead of the index, it's going to sort it based on the weight. That's what it's going to do. And we say use the x1th value for xth row to sort it. And that sorts it. So this is ascending order by default. And this basically means 1762 is most associated with the negative type, the ALL type. And if I reverse this, then this is going to be the highest expression weight. This is going to be the highest weight, feature weight. And that means this gene, 6200th gene, is the most important for AML type. All right. And you can, take your time to understand the code later as well. But the important thing is that we get this amazing list of genes, top 15 AML. So top 15 gene with the highest expression, sorry, not expression, I keep saying expression, highest weight, feature weight. So highest feature weight, as we saw, 6200 is most associated with AML. And then what I'm doing is I'm also appending to it the gene description and gene accession number. So I'm actually not appending. I'm using the first column so I can show you the indices. So this is going to be the list of those indices, top 15 ML indices. And I'm getting the genes table using index as top 15 ML indices, this vector as my indices. So it's going to give me the 6200th gene first, then 1778th gene, like that. All right. And this lists all the genes that are most associated with AML. Then we get the genes that are most associated with ALL. And we can make the same heat map that they had kind of made. Not sure if you're going to have many same exact genes. But in our model, according to our model, this is what we get. So for our model, this is what this indicates that I think I would draw a line maybe here. Yeah, so these 15 are ALL associated, and these 15 genes are AML associated, right?
And if I'm not wrong here, using like H-clust or some kind of hierarchical clustering.
We're not using hierarchical clustering. We're using the feature weights of the logistic regression model. So higher the weight for that gene. So
well,
basically,
sorry, I meant just for drawing that line. And
for that line. That would have been a nice approach too, actually. Clustering is also great. But basically what I've done is here, I've just appended the top 15 AML ones with top 15 ALLs ones. I've just appended them. Yeah, I just put them, I just stacked them on top of each other. Just to produce that. Yeah, I horizontal stacked them together. That's all I did. So yeah, I mean, that's basically the figure, and that basically shows us what genes are more important for ALL and what are more important for IML and AML. Yeah, I don't know how many of them actually match their papers. It'll be cool if we can get some. So I see IL-8 here, and it's associated with AML, right? It shows higher expression for AML. And we have IL-8 here showing higher expression for AML as well. Yeah, that's pretty cool actually. So it's showing higher expression for AML. We have the same, I follow the same order basically, just to kind of make it look similar to the figure they made. So this is AML. And these individuals are, that's what clustering could be useful for actually, Alex, but as you can see in the figure, like AML types are on the right and ALL are on the left. So I think 26, yeah, they had 26 ALL patients, and then in the training data set, and then the rest were AML. And you can probably even get this figure for more patients, like you can combine the training and test maybe. I don't know why I visualize this on training. It probably actually makes more sense to visualize it on the whole thing together, honestly. It is what it is. But yeah, essentially this is a cool representation. Train STD. Okay. Yeah, this one, right? So I can probably so yeah, I think I can combine trainx ilog indices. How many? Yeah, I'll have to get test. I was planning to like combine the training and test samples, but yeah.
I just have
yeah.
one quick thing.
Yeah.
I mean, this is just for data visualization. But
Sure.
the color map varied this too is really cool. I don't know if you could show it really fast. I always use it in R, and it's really good at I forgot what it is, but it's like a more linear difference
Yeah.
in like each
So-
unit of distance in the color is like
Yeah.
fully standardized. So
Which one is it? This one you mean?
yeah,
Bullhorn.
VIRIDIS.
Wait, I don't know if
I
capital.
just tested it. It would work.
Huh?
I just used it. I tested it.
Is it the small letters?
Hmm?
Small letters, like a
Yeah.
lowercase?
Just like that. See it in the chat.
Oh, VIRID. I haven't heard of that. Let's try it.
I think it's a very pretty one. It's good at
Yeah, I can kind of see it. Yeah.
I mean, it's not
pretty-
it's not really used. I think like the heat map
I think it's better for like, as you said, it's probably better for like linearly varying data.
Yeah, it's
But
just good at
yeah.
differentiating things pretty well. But I know for these kind of heat maps, usually it's cool warm.
Yeah, for kind of heat map with like, well, I was first of all, I was just trying to replicate this figure.
Yeah, yeah, no, most bio things use cool warm.
Yeah. But the reason I had, I think cool warm is pretty cool is because it's better at differentiating two different classes. This one has like yellow, then green, then blue, and then purple, right?
Yeah, and then like
So
upregulation and downregulation.
yeah, it does. I can totally see that. So, you know, we have upregulation here and upregulation. Yeah. Um, yeah.
Yeah, so I don't even know if it's better for this, but it's just a cool color palette.
All of them are great, I think. All of them are great. Yeah, so I hope you like this figure, by the way. Do you have any questions?
I have a question.
Yeah.
I think I got a little bit confused in the process. So originally we had a lot of genes and then a couple of columns of samples. I think it was like
Originally.
70 something, and then we cut it to 38.
Yeah, right.
So you said the coefficient thing or the weight array is for each gene instead of for each sample.
Yeah.
So
Yeah.
there's a
So
little
I
bit.
can, yeah, yeah, first finish your question actually.
Oh, so I'm just confused how we ended up with this graph. Wait, hold on, let me rephrase that. So I don't understand like how all those index for the coefficient thing ended up corresponding with genes.
Right. So, yeah, I basically see two questions. First of all, actually, from the original data, I hope you understand how we had just actually 38 samples, 38 columns, which are actually expression levels. All the other 40 columns were other stuff. Um, so that was how we got the 38 rows in train and 34 rows in test. Now, for each gene, so there are 7,129 genes. And I think this equation shows it basically. This is what the equation of the sigmoid function that we're trying to fit is. Here, um, each x is each feature. Okay, so x0 is the first gene, then x1 is the other gene, and so on. So you have many genes. For each gene, will have a weight, all right? And we don't know what those weights are going to be. Uh, Essentially, these weights are what makes this equation. Like in a linear regression model, suppose you have y equals like maybe wx plus c. I'm going to say b actually. It's the same thing. It's a straight line, right? If w gets higher, my line is going to get higher in terms of slope, right? And if b increases, it's just going to translate upwards or downwards, right? If b changes. The sigmoid function has some parameters as well. And those parameters are the weights, similar to this w. Instead of having a single weight parameter, this has a weight for each feature. Here we have one feature, x. Okay, we have just one feature, so we have just one parameter. And now we have a parameter for each feature, essentially. And this is actually the basis of neural networks too. We have a parameter for each feature, and then there's a bias, right? And it's gonna try to fit the equation, which means it's gonna try to find the W's and the B's, which best describe the distribution. Now, what I mean by distribution is that if I have the different data points, all right, so right now just imagine X to be the weighted sum, this thing basically, this sum, all right. So for any given sample, it has certain X values, right? And I have some parameters that gives rise to this equation. Um, and each point, each sample basically, when put into this function, gives some points like this. You know, we have actually it's going to be either this zeros, so like ALL, right? Data points for this. And then we're going to have AML types, which is one. And we're trying to fit an equation. You know, maybe we start with something like this. Then we come to something like this. Then we come to this, you know, that's what we're trying to fit. All right. So when we fit, basically we have found the W's that best explain the data. Now, the higher the value of this weight is, um, that gene, right? That gene is contributing more towards the positive class. Okay, and the more negative weight is that gene is contributing more towards the negative class, because um, if the gene expression changes, right, by a unit, how much will this z, this is not x actually, this is z, how much will this shift by? The W of that, the weight of that gene. For unit um, change in the gene expression level, right, the Z value shifts by that weight, because Xi is changing by 1. So the whole thing will change by a Wi, because it's multiplied by this weight. So if Wi is higher, right, a very small increase in the gene expression of that gene, it shifts this Z value towards the right? And as we go towards the right, the sigmoid is going closer to 1, right? So if a gene is, if higher expression value level of a gene gives a higher sigmoid output, I guess, that means it's giving a higher probability. And if it's closer to 1, we're predicting an AML. So that's why higher the weight, the more important that feature is for the positive class. The more associated that feature would be for positive class. Does that make sense, Cardiff, kind of? Yeah. All right. Yeah, and you can let me know. It's definitely hard to like understand this without taking like an actual machine learning class, but I hope I'm able to explain it. I'm yeah. I probably need to take more machine learning teaching experience as well, but yeah, this is my best explanation for the weights as importance. Higher the weight, more the importance of that feature for positive class, and more negative the weight is. That is the lower the value of the weight is, it's more important for the negative class. All right. Any other questions? Any question? Do you need further clarification, Carter?
I think in Aditya too has taken
Huh?
quite a lot of machine learning classes. I don't know if that'd be someone to follow up further with.
Yeah.
Um,
Yeah, I would say even the basic machine learning class 151, think it's a good start too. I would also say, like, if you already understand machine learning, then 151 might feel a bit too basic, depending on the professor too. Different professor has like different kind of flavor. Um, when I took it, I think we kept doing classification, didn't get to clustering or regression with the professor I took it with. It was pretty basic, but it was nice to actually focus on the basics like logistic regression and other algorithms and implement them from scratch. It was nice. 151A actually, yeah. 151B is deep learning, which is also great, slightly more advanced, of course. This is not top 10, it's top 15.
Okay, well, I need to get going.
Yeah, I think it's nice to wind up actually. Thank you so much for everybody for joining, and
Sorry,
I
can I ask a quick question? Let's like not relate to the content. Sorry about that.
no worries. But let me stop the recording if that's the
Yeah.
case. Okay, I'm gonna just to stop the recording. I can stop my share. Thank you, everyone.
Yeah, have a